please.
Awesome. Thank you very much. First of all, I would like to thank the organizers for having us here. Our talk is going to be slightly different than the previous talks. It's going to be more from the perspective of blue teamers and data scientists and their approaches to security. So without further ado, I'm Michael. My colleague here is Vojta, and we'll be presenting on command line obfuscation detection using large language models. Let's get right into it by looking at a few motivational examples of what we've detected using our language model, and then we'll look into the intricacies of how the model works and how we have achieved the detections. So what are we looking at? We are looking at a command line that has PowerShell pasted on it, which is a PowerShell script. Under normal circumstances, this wouldn't really trouble me in any way because it's quite often used by system admins for various automations and so on. So it's nothing really suspicious. And if we were to look a bit closer and analyze it, we notice that all the function names are completely normal and there isn't really anything unusual happening there. However, if we look a bit closer to it, we notice that all the variable names are really obfuscated, and this is raising a red flag that we really need to analyze this further. So let's look at what the script is really doing. First, it downloads a zip file from a URL. Afterwards, it unpacks the zip file into a DivX folder and mimics a DivX player. And last but not least, it writes into a registry to gain persistence. After analyzing this a bit further, we actually found out that this is a clear fake malware, which is a fake browser malware that impersonates browser updates and usually uses drive-by techniques for infecting various machines, and is quite often used as a stager for StealC and Luma info stealers. These malwares were developed by a Russian community that is specializing in info stealers. They are primarily trying to collect sensitive information such as banking details, personal information, credit cards, and so on. Under normal circumstances, you would try to detect this using IOCs, and as you can see in blue, there is a URL. So we analyzed this URL a bit further and actually realized that the URL was first registered 2 years ago and was parked up to the point of the execution of the script you can see. So a traditional approach of using IOCs wouldn't really work because this IOC wasn't really available in any of the feeds. So that's why it's really important to detect the obfuscation. So let's have a look at another example of what we detected using our LLM. We are currently looking at a execution of Windows Terminal. It's essentially a variant of cmd.exe on Windows 11, and I don't think you can read anything out of it, what it's really doing, so we had to analyze it a bit deeper. We reconstructed the process trees and actually realized that it's a new technique that is being used by the Raspberry Robin malware. The Raspberry Robin malware is a worm that spreads using infected USB drives. As you can see here, it was an infected Kingston flash drive. Afterwards, it executes a cmd.exe script along with the new technique we detected. And then it installs, lastly, a malicious payload from the C2 using MSI exec. Raspberry Robin is a malware that we don't know the full potential of yet. So far, we think that they are just testing the waters of what is possible. However, we've seen that it dropped Sogolish a few times. But it's using the infrastructure of infected QNAP devices. Therefore, you could potentially detect the malware using an IOC because the format of the QNAP management console usually is very similar. So let's look at our last example. And we can see right away that this is completely obfuscated and really suspicious right at first glance. And after analyzing it, we found out that it's the Ducktail info stealer that steals browser cookies, then takes advantage of authenticated browser sessions, and ultimately hijacks the account. This malware was developed by a Vietnamese group, and they're primarily focusing on hijacking Facebook business accounts. So, as we've seen, it's really important to detect obfuscation, and it's a great way to actually detect new types of malware without using IOCs. So let's first take a step back and look at what actually obfuscation is. Obfuscation is a technique to make code intentionally hard to read, but you won't change its functionality in any way. It also has a few legitimate use cases. For example, you would like to obfuscate your code so your competitors can't really reverse engineer it, or at least make it a bit harder for them. But of course, this is a double-edged sword. APT groups such as APT32 or Ocean Lotus or Sea Lotus, under whichever name you may know them, they're actually using this technique quite heavily, and it's a military group that is actually focusing primarily on attacking machines in Cambodia and the Philippines. So let's look at what other techniques of obfuscation are out there. I'll just list a few. The first one could be using environment variables. So you set an environment variable and then just reference it, and the script executes without any issues. Another one could be inserting garbage delimiters that you remove while executing your script. Or you could add special characters that are actually being ignored by the Windows command line, such as the caret symbol or the tick symbol. Or you could also just change the case of all the characters that are on the command line, and this works totally fine. And I could really just spend hours on listing the different techniques of obfuscation that can be used. And really a big shout out to Daniel Bohannon, who had an awesome talk at Black Hat covering all of these techniques and tactics. And also he has a great paper covering all of them. So let's get into the interesting part, which is the detection. But before we look into detection, we first need to define actually what data are we working with. We are specifically working with command lines only, so we aren't focusing on script contents, just pure command lines. And we have narrowed it down to living of the land binaries. So, for example, it would be PowerShell, CMD-exe, WMIC, and many others. And you can see the examples on the bottom part of the slide. And what would be a traditional approach for detection? So let's say this is a command line or some malware that you would like to detect. Normally, the first thing you would try to do is try to look at the hashes of the executed binaries. But you see that here it's CMD-exe, which is a legitimate binary that is pre-installed on Windows operating system, and it's signed by Microsoft. So this is really off the table. So let's say that we analyzed multiple instances of this malware and found out that it always has CMD-exe on the command line, then without, and hashtag stealthy. So then the natural next step would be to write a signature, which is quite easy. However, if we were to change just one character, for example, W, and as I said, you can change the case of the characters in whichever way you want, you would be able to actually avoid detection. But this is still easy to solve. You just add ignore case. So let's look at a different example. You add the caret symbols and tick symbols into the command line. So this is already becoming a bit more complicated, but it's still doable, and it's already becoming quite ugly and computationally expensive. However, if we were to add the environment variables, I think you get the idea, and this is not really a sustainable approach to detection. Therefore, we really need to find a precise, fast, and smart way to detect obfuscation. And with that, I'll hand over to Vojta.
So, hi everybody, and I'm here to talk about approaches that you could take from a machine learning perspective. And so let's first define what actually we want from the detector, so how it's supposed to behave. So we have three main requirements for a detector, which is it needs to be smart, it needs to be precise, and it needs to be very, very fast. So let's dig into it a bit deeper. So what does smart mean? Smart means that when you perturb the obfuscation a little bit, like the detector is not going to fail immediately. can in-depth analyze the command line and the components of the command line and how they interact within each other. It needs to be precise because everybody is aware of the alert fatigue that the security systems are providing for all of their customers right now. And if the model is not going to be precise, then everybody, like nobody's going to be paying attention to it, and nobody's going to go through its outputs. It also needs to be very, very fast. We want to be able to do this at scale. We want to process like hundreds of millions of command lines a day, or at least like tens of millions. So we cannot have something that doesn't scale well. So what would be the two common approaches? There would be the bag of tokens classification or sentence classification. We'll go through both of them, and let's start with the first one and why not to do that. Yeah. Right. So on the left-hand side, you have the general procedure that you would follow in this kind of classification. So, and on the right-hand side, you have an example. So first, let's go through the general procedure. Your input is a string of the command line, which you split first into a group of tokens. Then you have a group of tokens, and you need to extract some information on top of that. So you would want to characterize of what you actually have on the input. And you design a set of features that could be like tens of hundreds of features, depending how patient and creative you are. This would result in a list of numbers, so-called the feature vector, which you would then feed into a common classifier standard that would try to like differentiate the two classes based on provided feature vector. So in practice, it would look something like that. You would have the hello world example. You would split it into each respective character. You would completely disregard their order and their meaning, and then you would perform the important part, the extracting information, right? So you would count, how long was the command line, the number of caret symbols, the number of dash counts, the uppercase count of the number of uppercase letters. And you would hope that these things would, distinguish the two classes very well. And then this would result in a list of vectors which you would feed, for instance, to decision tree or random forest classifiers. So what is the problem with this? Well, it's the red rectangle, and that's it's really, really painful, and it's almost impossible to design this very well to distinguish these two classes because it completely disregards the semantics of the command line. And you could, we've been through that. It's really, really it's really, really painful, and it will not get you anywhere. Out of our 3 requirements, it basically fails 2 of them. It's not smart because, if you just change the order of the characters, then it will produce the same outcome. It's not precise. It produces tons of noise, but it is fast. It's very fast. I'll give it that. But we need to do better. We need something much, much better in order to be successful at this task. So we're left with sentence classification, and let's look at what I mean by that. So in sentence classification, basically you again split it into tokens. Could be letters, could be bigger units of meaning, as we'll see later on. You keep the order of the tokens, and then you say, okay, I'm gonna say that this command line and the representation in which I split it, I'm gonna say this is a sentence in a very, very gibberish language, which is the command line input language. And we all know which models are lately used for analyzing languages and interpreting languages, and that's the transformer-based language models. And that's, for people who do not know that's the architecture on top of which all the new hype models such as ChatGPT and Claude and all of that are built on these kind of models, because they are very good at analyzing sequences of tokens. That's what they do. That's their bread and butter. So we have decided to build our own custom model for the command line. For the command line input, in hopes of that it's going to be able to detect the obfuscation. And we'll go through four phases or 4 things that we need to achieve, we need to go through in order for the model to be successful. So first, let's start with the pre-processing phase, and that's a phase where the model doesn't actually see any of the input yet. We just need to get rid of some noise in the input. So in this phase, we want to denoise the input from anything that is not important for the command line obfuscation. So, it doesn't matter which particular date there is. So we would, for instance, find all the dates with, classical regex matching, and we'd replace it with a general token that would just inform the model that a date was present here. We have actually a lot of these that we've identified, and even before any parts of the model see the input, it gets denoised in this manner. So we replace all the URLs, we replace the dates, GUIDs, numbers, IP addresses, and so on and so forth, to kind of, so the model doesn't have to learn redundant information. Then the next step is the tokenization phase. Well, as before, you have an input string, and you still need to tokenize it. You still need to break it down into units of meaning. So how you do that? We've decided to go with the natural language processing standard for language models, which is the word piece algorithm. So you gather tons and tons of command line data, basically as much as you can. You shove it into the word piece algorithm. It performs frequency analysis. It pieces together characters and tokens to create tokens that are much more prevalent in the data, and basically it spits out the token vocabulary, which then you can use in your tokenizer in the following way. You have the pre-processed string on the input, and you supply the token vocabulary, and the tokenizer splits it into the tokens that the model is supposed to learn. The model is supposed to learn the representation of each token and how it interacts with other tokens that are in the data. And now this is actually the input that the model can chew through, and that the model is designed to work with. And we can finally go to the training phase, which is the important part and the most interesting part. So the model training phase is actually two phases, as is common with language models. It has the pre-training phase and the fine-tuning phase. The first pre-training phase is there just to let the model learn on tons amount of data, but it's supposed to just learn the rules of the language that it's supposed to work on. So, the common language models would just chew through tons of English text. In our case, the model would learn the command line structure. So we would employ a self-supervised task where no labels are necessary. At this point, the model hasn't seen any of the obfuscated stuff. It doesn't know that it's supposed to detect obfuscation. It's just supposed to learn what is in the data, how the tokens interact with each other, and because this will help him substantially in the later tasks. And we decided to go with the Electra pre-training, which we'll go through shortly. And that's for two main reasons. One is that it's very computationally effective, and that the pre-training objective, the task that the model learns the structure of the data on, is very closely related to obfuscation detection. So, what is the Electra pre-training? It's, in a simplified manner, it's the following. You have your pre-processed and tokenized command line. So it's just a bunch of tokens in a sequence. And let's say you take 15% of them. So in this case, you would choose the #exa token and the URL token. You would, in a simplified manner, random-ish, replace them with tokens, such as the #exa would get replaced with sys token, and the URL token gets replaced with the uppercase C token. And you know which tokens you replaced. Those are your labels, and the model is you supply this to the model, and he is supposed to predict which tokens were replaced. So he needs to learn which tokens do not belong where they are. And through this task, it learns the command line structure, because it does this on millions and millions of command lines repeatedly. And as it gets better at this task, it learns which token belongs where and which doesn't. So this is the pre-training phase, and then comes the fine-tuning, which is the most important part, because at this point we are actually tasking the model with detecting the obfuscation. And as with most machine learning tasks, the most important and most interesting part is the data set that the model is trained on. And so we're using the pre-trained model from the previous phase, and our data set consists of two classes. All of them belong to samples from our telemetry, and that would be like production data from EDR solution of Cisco. And so you would have the obfuscated and non-obfuscated samples. The benign, the non-obfuscated samples would be just a normal telemetry sampled from samples sampled from the telemetry. And then you would have like one obfuscated sample for 30 benign samples. So in total, we have around 600,000 samples in the data set. But the obfuscated samples are very, very rare. Like it's like in the wild, it's really like hard to find them. So in our data set, the obfuscated samples then again divide into two categories. First of which is the samples from telemetry, which actually went through hands of people who know what they're doing, so cybersecurity researchers and cybersecurity engineers that have identified them in our telemetry. Those are the most important and most valuable samples for this training, and the most hard to come by samples. And since like these were not enough for the model training, we have included also the artificially obfuscated samples, and we have done that thanks to the invoke obfuscation framework from Daniel Bohannon, which Michael already mentioned. He developed this framework, and it's for like you supply it with a command line, and you can highly customize it with like all kinds of parameters, and it obfuscates the command for you. So we would get some of our telemetry, and we'd artificially obfuscate it with this framework, and that would consist that would like be a large part of our data set. And it was super helpful because it helps the model to learn the technique and not just particular examples of obfuscation. So how these samples would look like is shown on this slide. The initial command line that we would supply to the framework would look accordingly. So first you have the light level of obfuscation, where you just change some uppercase and lowercase letters to make regex matching harder. Then you have the medium, which you add some caret symbols, some tick symbols. It's getting harder and harder to read, but it's still quite okay. Then you go on to the heavy obfuscation, where you introduce some arguments. It's getting pretty messy, and like then you have the ultra obfuscation, in which even the base 64 is obfuscated into base 8 times 8, and you can really tell what's going on. What is actually interesting that we mostly focus, or like our biggest focus, is on the light and medium obfuscation, because that is hardest to detect. Like all the statistical approaches might get a chance at the ultra obfuscation, but the light and medium obfuscation is very hard to detect and is most prevalent in the data from what we have seen so far too. So that's the stuff what we focus on. So this is the data set that we trained and then fine-tuned the model on, and it was actually quite smart. The first requirement was satisfied. When you play around with it, and you can see that it can detect new types of obfuscation, it can detect like if stuff that it hasn't seen before. Issue is like, just imagine that during its training, it has seen around 600,000 samples. Well, in a daily mode, the model would see tens and maybe hundreds of millions of samples each day. So it got to see only a very like specific subsample of the data. So at this point, it actually wasn't precise. It was producing a lot of noise, and we were really not satisfied with that. It was like 1 true positive to 300 false positives, and you cannot like output any model like that. So we have designed this, like we followed on with a procedure to fix that in the following way. We took the model, we let it evaluate it. We let it evaluate on like 5 to 10 days. And then the painful part comes, and it always comes in these projects, like machine learning projects, where you have to manually label what the model has produced. So you'd take the stuff that it marked as obfuscated, and you would manually go through them. You would label it, and that would create your evaluation data set that you want the model to improve upon. But it is also like quite tricky from the machine learning perspective, because the evaluation data set is heavily skewed. Like, it doesn't represent the distribution of the data. It's just like what the model has triggered on. So it's a bit technical. I'll be happy to talk about it, but we don't have time for it right now. You have to make sure that the model in this phase doesn't overfit on the evaluation data set that you have provided, because it will like stray away from what it has learned during the previous phase. But this procedure has like heavily improved the model. Actually, very surprisingly, even that we then evaluated it on like 10 to 14 days of telemetry, and it was able to achieve precision to like 70 or to 75%. The evaluation would be on like 540 million of command lines, and like tens and tens of Cisco customers. All the evaluation is on production data from real network. It's not just some lab. So it's like it has done pretty well. But we have like left out one very, very, very specific, very important part of it. And it's like, I haven't even touched how big or fast is the model. And transformer-based models are notorious for being computationally expensive and that you need a lot of GPUs to run it. And, so let's have a look at that. Like many of you will probably know the BERT-based model, which is the father of all language models and transformer-based architectures. And that, the base model has around 110 million of parameters, and we had the advantage that we had everything customly coded from tokenization to from pre-training and fine-tuning, so we could experiment a lot with the model size. And we have actually, quite surprisingly, we've been able to get the model down to only 115 parameters. 115,000 parameters. So the model is like really, really small. It's a dwarf compared to all the other transformer-based models that are out there. But it turned out that for this task, it was enough. A lot of you may not know the BERT model, although, but everybody is going to know the ChatGPT Model 3. So we can also make a comparison of the BERT-based model, which is already 1,000 times bigger than our model, to the ChatGPT 3 model, and it basically looks like this. It's the ChatGPT 3 has like 175 billion parameters, and the ChatGPT 4 I think is like also 1,000 times bigger, or something like that. So, but let's get to real numbers. How much data are we actually able to process it, or like process with it? And on like a cheap middle-range GPU, which is the NVIDIA Tesla T4, it's got only like 16 gigabytes of RAM. We're able to process like 18.5 millions of command lines per hour in like AWS hosting solution that would equate to like $0.5. And you know, a lot of people will probably immediately go and like, okay, but why not use like ChatGPT 4 for obfuscation? Because with some prompt engineering, you probably could force it to like give you some good results. Well, we've counted the number of tokens and like approximated how much that would probably cost for like this 1 hour of data, and it would equate to around $33,000 at least. So, and the processing time is like, yeah, give it a shot, you know. So the model is very, very fast. It's we have come to a point where the model is smart. It's able to detect new stuff, like Michael was talking about, all the hits. It's very precise. Like the 75% precision rate on such a huge volume of data is really something that we're proud of. And it's also very small. It's very fast. It's actually so fast you probably run it on a toaster and in like IoT. And last thing, but at least, is about how we deploy the model, how we actually do the classification with the model. And we have two modes for this. They both run with the ONNX framework, which is a popular machine learning library. First, we have the stream processing framework, which is like a Flink streaming framework. It's run only on CPU, which is completely feasible due to the small size. It produces real-time security events. It's written in Scala. And then for evaluation and monitoring, we have also the batch processing, which is hosted in AWS Airflow, which is super, super convenient for any kind of work with these models and large data. It runs like an hour a day or something like that on GPU, on the middle range GPU, and produces daily results for researchers to analyze. And that's written in Python. So I conclude my part with this, and I'm going to hand over the last couple of slides to Michael.
Thank you. So one may ask, how do we do this in production, and how do we do this in real time? We created a Apache Flink pipeline, and we wrote the pre-processing as a simple function. Then we managed to port the tokenizer from Python using the deep Java library. And last but not least, we use the ONNX framework for the model itself. Like this, we're actually able to provide the alerts or security events in real time without any delay. And it's actually quite cheap because it's able to run just on a couple of CPUs along with 130 other detectors. So it's not really the only thing running there right now. So to conclude, I think we created a smart, precise, and fast large language model that is actually very cheap to run compared to other approaches. The precision we have achieved is quite good, and we've actually managed to find quite a lot of new interesting hits and also some new malwares and IOCs. We also are quite confident that we would be able to detect some of the obfuscation methods that were actually presented here at the conference. So, red teamers, be aware. And what are the next steps? We would really like to focus next on creating a similar type of model for the Unix-based operating systems such as Linux or Mac OS. The techniques there look quite a bit different, so we may need to change or modify the model. We'll see. Then we also want to try a actually large language model and compare how it would actually perform in real time. And last but not least, we are working on collaborating with other threat hunting teams within Cisco, and we are providing them with the intel we gather using this approach. So I would like to thank you for your attention. My name is Michael. This is Vojta. Here is our contact information, and we are happy to open for questions now.
Thanks a lot for your nice talk. Yes, we have plenty of time for questions. Please don't be shy. Any question for them? There are 2 questions. You can give the mic on the right side. Great.
So, thank you for the nice talk. Does that mean that for doing obfuscation, we should obfuscate everything that is looking like IP addresses now?
Well, you might do that, but then the regexes are not going to hit on the IP addresses, and then it's going to stay in the command line, and the model is going to see it.
There was another question. You have the mic.
3? Yes. Thank you for the talk. Very nice. When you created your model, did you start big and then downscale it to that small size, or how did you achieve the great performance on that such a small model?
Yeah. Basically, that was the case. We did start big, and we have just kind of since we are constrained, for scaling purposes, we really try to get it down as much as possible. And this is we have done some testing on how slow we can go with the model. This is the learning curves for one epoch. So I would say we have observed the performance on training and testing data sets, and we based our estimate on top of that. So we have done a lot to downscale it as much as possible, especially for the streaming framework, because that's it's hard to run it with everything else, so it needs to be downscaled as much as possible. Yeah.
Thank you. Any other question? Don't think so. Well, thanks again.